Okay, so good morning, and we're going to start lecture number 35, which is most probably the last lecture, and we'll continue our study of the magnetic properties of Fermi gases, basically. Okay, and last lecture we did the high temperature susceptibility. We computed a few other things along the way, and I'm just writing this in a particular form. So probably I didn't write mu b, but it was there as EH bar upon 2m whole square, like this. And so now I'm just writing it this way. So, okay. So what we will see is that if we, in the second part, we look at the paramagnetic contribution. Again, it will be, the prefactor will be exactly this, but this minus 1/6 will become, I think, plus 1. Okay. So you can see that when you add them together, the overall effect would be still paramagnetic, because 1 minus 1/6 is 5/6. Okay, but what we want to do is something, before we do that, what about low temperature behavior? Okay, so in particular, we'll focus on, I won't do T greater than 0, because T equal to 0 is interesting in itself. Zero temperature. Okay, so we already know what happens, right? Even in the absence of magnetic field, what do? You fill up things up to the Fermi level. Okay, so the question here would be, we have to locate, once you turn on a magnetic field, we have these Landau levels, and we have to start filling from wherever, and it'll stop at some point, right? So at T equal to 0, the system is in the ground state. Okay, so we saw the single particle spectrum was like this. So in terms of some energy divided by H cross omega C. Okay, so in those units, the first one will be half, next will be 3/2, 5/2, so on and so forth. And the NL values for these will be Landau level 0, 1, 2. Okay, and the degeneracy is a Dirac delta function, if you wish, if this is degeneracy. G for each of these things. Okay, and what is G? G was 2 for spin times BA divided by phi naught, which is the flux of the thing, H by 2E. So this guy will be BA into 4E by H. Okay, these are formulae from last lecture. So now the question is, so we have n particles. Okay, and so we'll start filling these guys, and so in terms of energy, this is the lowest. So you would fill these guys and you would use up G of the things. Okay, so let us assume that all Landau levels with NL equal to 0, 1 up to some J are fully filled. Okay, so that means J plus 1 of these Landau levels are fully filled, and whatever remains will be in the next, okay, the remainder of the n particles how many of them would be, which is n minus j plus 1 into G will populate the NL equal to j plus 1 energy level. Okay. So question is, what is J? Okay. So we know N, we know if you fix B, so we can write J as follows, rather J equal to, I'll write something and then N by G, I think, minus 1. Okay, or J plus 1 is this. Do you know this function? It's the floor function. Okay, so floor function is just the integer part. Okay, so if you have something like this, it will be 2. What is this? 3. Okay, so on and so forth. Okay, so this just tells you that, so N by G will tell you how many are filled. That should be J plus 1. I just pulled it to the other side. Okay, so this formula works. Okay, so in particular, what we will see is that there will be some inequalities which I can write. So let us define some things. Okay, so also we can write this inequality, which is J plus 1 into G is less than N, which is less than J plus 2 into G. Okay, we can rewrite this, or this is a useful way of writing this. 1 by J plus 1 is greater than where B naught is nothing but N by G or G by N. Okay. B by B naught is B naught is come here. Yeah. So it's really this term. This we'll call 1 by B naught. What was it? H by 4E into area. Into N. Aha, okay. Yeah. Okay, so this is just a definition. And but there is some significance for B naught. Okay, and I'll explain that in a moment. Okay, so when B is greater than B naught, okay, so what we are doing is in this here I'm just thinking of varying B and keeping N fixed. Okay, so when B exceeds B naught, okay, what we can see here is that no, if you look, no, there is no Landau level that is fully filled. Okay, so everything will fit into in other words, every electron fits into the lowest Landau level. Sometimes people write triple L for this. Is this clear? You can check this. I mean, you can ask. Okay, this is what. Even if you look at the inequalities, you will get it. Okay, so this is what you have. So that's the significance of B naught, and we will also define alpha. Okay, to be B by B naught. And the interesting thing, so more and more when alpha is less than 1 is when more and more Landau levels will get filled. Okay. At least 1. Okay. And you can also see that this every time there's a Landau level getting filled, there's a jump happening. Okay. And one more thing I forgot to write in this picture is the spacing. Oh, I've written the spacing. I wrote it in terms of h per omega c. Okay, good. Okay. So this is what we have. Okay. So now we know what the filling is. You give me the B and n is fixed. We can compute alpha and see how many Landau levels are filled. Okay. So let's do the case. Okay. So first let's do the ground state energy. For various cases. So first one is just alpha greater than 1. Everything is in the lowest Landau level. And what is the ground state energy? Anybody? Into n. Okay. And just remember that omega c was EB by m. So there is a B dependence. So this E0 is a function of B. Okay, good. So second case is alpha is less than 1. Further, that inequality, which is 1 by j plus 1, greater, I think. Okay, that means this implies that j plus 1 Landau levels are filled. So now we should start. What is E naught of B? Okay. So we have to sum over NL equal to 0. So up to j they are fully filled. And each guy can hold G, guys. G into NL plus half H cross omega C. Okay, plus. Now the stuff in the j plus 1th guy, how many are there? It is n minus something, right? Plus n minus j plus 1 into G times, and that would be NL is j plus 1, so it is into j plus 3 half H cross omega C. Is this clear? So I've just worked out what are the remaining things they're lying in this thing. So this is from the j plus 1th guy, and these are. So now these are sums we can just do. We just need to sum here over NL. Okay. So that's also not hard to do. So this is equal to, I'll carry out the sum. So sum over NL from 0 to this thing. So that will be G into J plus 1 by 2. Okay. And plus half these things would be just J plus 1 into H bar omega C plus. Okay. And we also have a contribution. I want to pull out the G contributions out here. So there's one more G out here. So if I put that here, that will be just minus J minus J plus 1 into J plus 3 by 2. Okay. Plus N into J plus 3 half H cross omega C. Okay. I've just rewritten the term. So now you can simplify it, etc. But we will also do one more thing. We'll pull out an overall factor of n. Okay. So, and we need to check what G by, yeah. Okay. B naught is this thing. And this is what 1 by G, yeah? Is it? N by G. So B by B naught. Yeah. So let me just, B by B naught is, I think it should be G by N. Okay. So I can do that also. I can pull things out. So I'll pull out an overall factor of N. Okay. And so this G by N is alpha, right? And what does this simplify to? Mine. Let me write it. Yes, I'll write it in a different way. So we are putting in the formula for omega C. That is this. H bar, this is H cross omega C. I pulled out this N, so that takes care of these factors. And now we just have to write stuff. Okay, so here you can just check that this will be negative this term, because this, look at large J, this goes like J square by 2 minus J square. So there'll be a minus, it goes like minus J square by 2. So I won't write this term first. Okay, so this is just, so I've just pulled out these things. So what we will get is a J plus 3 half. Okay, and there'll be a minus. There is some question. Somebody said present. Okay. And so the minus part will be, sorry. Ms. Dinesh, can you please mute yourself? Minus half. Okay, this is what we get. This is the answer. Okay, so now you can see here that E naught of B has two dependencies on B. One is here and another is here. Okay, so that's a quadratic term. Unlike here, where there was only a linear term. Okay, so this is so life is now simple. We can now, so what is magnetization? It is nothing but dE. I think d. So it's minus mu dot B, right? So d minus dE naught by dB. Okay, and chi would be minus d square E naught by dB square, evaluated at B equal to 0. Okay, so let's first do the easy case. Alpha is greater than 1. Okay, so then M would be Did I miss any volume factor? No. Hmm? This one. Thanks. So M would be H cross omega C, which is E. Okay, fine. Okay, yeah. So, and we can also compute M by V, and then this will become little b. That's all. Okay, and chi is 0 because it become a constant. Okay, what happens when alpha is less than 1? Okay, now there is a quadratic piece in B in the expression for E naught. Okay, so magnetization M, which is minus d E naught by dV, will be a formula which is slightly messy but not terrible. I'll tell you what X is in a moment. Okay, and X is alpha actually. Okay, this is what we get. Okay, so you can see it has different values depending on J, and this, if you plot M versus B, it will be some straight line, and this will be the slope because this alpha is B by B naught. Okay, so that's one thing. From this we can also do chi, which is taking the second derivative, and that will just give you N E H bar upon 2M into 2J plus 1 into J plus 2 divided by B naught. This term drops out, which we can simplify to be a little bit better. Why one? I won't simplify. Leave it. So that's it. So this is what we have. Okay, so this is a constant which depends on J, and you can see that as J increases, the constant the value goes up. Okay, so that's what you have. Okay, so M versus B is a straight line. With slope I'll only give, I mean, there is some constant, prefactor is the same, slope proportional to j plus 1 into j plus 2. I'm focusing only. Okay, so that's what happens. So just exercise, just plot these things. J equal to 0, 1, 2, 3, just a few things. Okay, so that you, on the same graph, you should plot those things. Okay, so this sort of concludes what we wanted to see. And now you can see that this chi is not negative, it's positive. Okay, but once you exceed, but it's negative for alpha greater than 1. So it goes from a diamagnetic thing to a paramagnetic thing. But that depends on the value of alpha. Okay, so I'll pause here for questions.
Sir.
Yes, go ahead.
So, a while before, in each row, at alpha, for alpha greater than 1, all the only the ground state will fully have this expression. Okay. Oh, okay. I have wrongly written it as NH omega bar C. So that's
Yeah,
why
I also wrongly wrote it and somebody corrected it for me. And so I put the 2 later.
Okay.
Okay. Okay. Thank you. Yeah, it's half H cross. Okay, good. Any other question? Okay. So we'll do the last bit, which is Pauli paramagnetism. So here it's just a contribution from the spin. Okay. Okay. So the full Hamiltonian would be what we did last time, would be 1 upon 2m p minus EA whole square. Okay. Minus. Okay. So okay. What is m? M here would be so I'll write it in terms of mu b into sigma. Okay, so where mu b, we have derived this long ago by 2m. Okay, so, and this is just a Pauli matrix now. It's a 2 by 2 matrix. That's it. Okay. The half has been absorbed into mu b. So sigma can take only plus minus 1. Even the spin half really is plus or minus half in units of h bar omega, but we have removed the h bar by 2 out fully. So so the eigenvalues of sigma is just plus 1 and minus 1. Okay, so it's like up-down kind of thing. Okay, so that's what we will get. So first thing is, we've already studied the effect of this. Okay, so we'll drop EA term in the KE. Okay, and that's what we will do. So H will just become, for simplicity, 1 by 2n p square. Okay, this is a one particle story, but okay. And B is along Z direction. So this will just become minus mu B times sigma C. Okay. So is this fine? So because we already considered the effect, we could do everything in, like I said in the beginning itself, we could have done everything in one fell swoop, but it'll be a mess. But we can put these things together and add the answers. But homework for you is maybe do it all together. Okay. So what we will do is we will work in the canonical. That's it? Oh, yeah. Thank you. Thanks. Okay, so we okay, we'll do that, and we'll do it in the following way. So let's so we have n particles. Okay, and let n plus minus denote the particles with spin parallel or anti-parallel to the applied magnetic field. Okay. So of course we have to sum over all possible configurations in the system. Okay. So let's do that. So we have n equal to n plus n minus. And one more thing is that the magnetization of your sample m will be equal to what? N plus minus n minus into mu. Actually, I forgot the G factor of the electron is 2. So I need to multiply this by 2. Okay. So what I will do is I'll just remove that 2 from here. But that's not correct. Bohr magneton has a 2 usually. So let's, I don't know how to do this. Yeah, let me, yeah, I'll call it mu tilde. Okay. So I just don't want to, I don't want to use mu because mu is used with chemical potential. And so there is some, so let's do this. Mu tilde, and mu tilde. It's 2. Did you derive this from Dirac equation? You can show this, that this coupling comes with G equal to 2. So actually it's very interesting that the original experiments, etc., they thought it should be +1 -1, whatever. I mean, because there's no half integral stories, Stern-Gerlach or whatever. And but what is happening is that it's true because the G factor 2 into half is 1. Okay, so it's a conspiracy which worked out right. But they didn't get the Nobel Prize for it. That is the sad story. Okay, so this is what we have now. Okay, mu tilde B. Okay, good. So now let's compute. Okay, so Z, and we have n particles. So let's put a subscript here. Z would be, okay, so we have to do a series of sums, of course. So if you're n plus guys here, so that will be n plus. Okay, this is what you get. Okay, and then we have, so suppose we have NP. We still have to do more things. I'll write some things and then number of particles in this thing. with momentum p, and e power minus beta p square upon 2m into np. Put a prime here. So this is just the sum over. So there are n particles with the momentum p. Np is that you sum over those things, and the prime indicates that the sum of those things should be equal to total n that you know. Okay, and let's do it this way. Okay, so here definitions are obvious. N plus of p is equal to number of particles with spin up having momentum p. Okay, and there's a the prime. Okay, similarly n minus p is number of particles with negative spin. Okay. There are primes here. Prime says that sum over all p. I'm acting like it's a discrete variable, but it could be continuous, and we replace it by integration. N plus p should be equal to n plus, and constraints should be equal to n minus n plus. It's n minus, but these are the constraints. Okay, so let's do some definition. So the point here is that what we would like to do is to carry out these integrations, these summations of these internal summations first. And we'll do that by defining something. Okay, so I need to come up with some notation. So the partition function of n spinless fermions Okay, that's what it means. So you ignore spin, and so what is the definition of such a thing? Z0 of n would be just something like this: sum over np. Prime again, that the summation of all those things add up to n. That's the same prime, e power minus beta p square upon 2m into n. Okay, so this is actually something which we have computed before in some sense. So then you go ahead and you don't do it this way. You write it as little z power n. We have done many ways of doing that, so we know how to compute this. Okay, so let's and this is nothing but e power minus beta f0 of n, free Helmholtz free energy of that. Okay, so now if you see here, if you look at this now you can see that this summation becomes expressible in terms of that. Same thing, second one can be written that way. So this says that Zn is equal to summation n plus equal to 0 to capital N e power plus beta into n plus, did I forget some b or something? There should be a b here. And somehow I went off so many pages below. Zn. Okay, so whenever I see n minus, really, even here, it's better to remember that it's better to n minus is n minus n naught, so it will become 2. So let's do it this way. Let's write it in terms of the variable n plus. Okay, this is our answer. Okay, so
Sir,
yeah, go ahead.
do we know NP as a function of P? Means it is the distribution of
No,
NP.
we want to sum over all possible momenta values of n. So it's like our regular integral.
Okay.
I mean, this is not the nicest way to do that. I mean, so we could go back and do, our semi-classical computation or something to get the z0 of n, right? We can do that. That will be also good enough. Okay. So all that is buried into this definition of the z0 n. Yeah. Okay. So somebody is asking question online. So, okay. So now we have to compute. We want to compute Zn, and so how do we compute it? More than that, we just want to compute actually 1 by a log of this guy. So suppose we want to compute 1 by log of Cn. Okay. So this would be so. So I'm just taking out this n-dependent piece out here and putting it there. But the other terms will have to be inside that thing. Log of summation n plus equal to 0 to n. Okay. E power beta mu tilde bb n plus 2n plus into e power, say, minus beta f0 of n plus minus beta f0 of n minus. So it looks like there's a whole bunch of summation, okay, and it looks messy to compute, okay. So what we will do is use a method which is standard saddle point, approximate this by the term which contributes the maximum. Okay, so the argument of the exponential is 2 beta mu tilde b into n plus, okay, minus beta f0 of n plus minus beta f0 of n minus n plus. So this is some function of b. This is some function. Okay, so let's call this function of what? Of n plus. Okay, so okay, because we are summing over n plus. Okay, so we want to ask, okay, so it's e power f. That's what we have, f of n plus. So now what we have is 1 by n with this complicated definition log of Zn just becomes this first term minus beta okay. Okay. So if you can figure out where f of n plus, okay. So let n plus bar, okay, be the maximum of f of n plus. Okay. Then what we will do is, then we will say that then we will approximate it as follows. We'll say 1 by n log Zn is approximately equal to so the summation I'll just replace by a single term f of okay, we haven't determined the n plus bar. Okay, so that's what we get. Okay, so this method is called the saddle point method. Okay, so we are just doing that. But there's a nice what is n plus bar? It is the most probable value of n plus. So that's truly, so really you're determining, and magnetization, so n plus bar is the max, the most probable value of n plus. Okay, so thus magnetization becomes very simple in terms of n. What is magnetization in terms of n plus bar? It has to be n plus bar minus this thing, so but we should write it in this form. Okay, so let's look at these, look at the definition of f. Where is it here? Okay, so we have to differentiate this with respect to n plus. Okay, so we'll get one term here, which is this, but then we'll get here f0. This is just that thing of the spinless gas, and we're going to do df by dn plus. What does that mean? That is just nothing but up to some factors. It's a chemical potential of df by this thing is the chemical potential by definition. Okay, so so I'll write an exercise, but and write the answer. Show that okay, df by dn plus equal to 0 implies the following thing, which is mu of n plus minus mu of n minus n plus equal to 2 mu tilde b okay. So this and we have formulae for this will be like, what is the mu we have to use? If it's high temperature, we will just use the standard, we can use the ideal gas mu. Okay, this minus sign is important because what it says is that I mean, that's because it comes like n minus, it depends with n minus n plus. That's the reason the minus sign comes. Okay, this is the answer. It's kind of cool, and it's interesting what happens when b equal to 0. Okay, so we can think of n plus and n minus are not fixed, so it's random. So we can introduce separate, two species are there, n plus and n minus, and you introduce a chemical potential, and we know in thermal equilibrium the chemical potentials become equal. And what this is telling you, if you turn on a B, there is a bias. So positive B means the chemical potential for n plus is higher, and that is also that it, okay. So this formula actually captures what we expect. Okay. So now we need to just go ahead and plug in formulas for mu b, etc. Okay. So there's a nice solution to this problem. So really I should put here, this is the value, right? That this determines okay. There is some more work to do, which is to take the second derivative and show that, that it has the correct sign. Okay. But that we are not going to do. Okay. So we are not done. We still need to determine. Okay. So there's more work to be done. And let me just summarize what we will do. Okay. Okay. So we know some things, at least at low temperature. For a Fermi gas, we have actually computed mu. We had this formula which said mu of n is equal to I'll write something and then we also work this out because pi square upon 12. I'm slightly puzzled why he has put in the book there's a 2n, but here's a formula. So this, so let's look at this. Yeah. So now I understand why this 2n is coming. The reason is that when we did the computations, when we do the computations for fermions, we didn't do it as spinless fermions, and we put a factor of 2, g factor of 2. I think that's this. Check this, okay? I think that's what's happening. Here also 2n. Okay, to match what we want is mu. We are interpreting it as a gas of spinless, so ignoring spin, g factor due to spin. So that is accounted for by looking at this. Okay. What? No, it's not 2 times that. It will go in with no. It will go with n. That's the point. Okay, where epsilon on of f of n is defined to be 3 pi square n by v over what? 3 by 2 or 2 by 3. So this is some computation which we would have done before. Okay, so you can go ahead and do this. So now you can use this approximate formula and solve for this thing. Okay, so let's so I'll just do it for simplest stories for t equal to 0. Okay. So then let's make a definition. Let R be 2n plus by n minus 1. Okay. So this is just the fraction. So if you look at R goes from 1 to minus 1. Okay. So it's just, it's n plus minus n minus upon n. It's the same thing. Okay. So R being 1 means all the spins are aligned along the thing. R equal to minus 1 is anti-aligned. Okay. So that's what it is. So you can show that this equation star becomes these are t dependent terms. Okay. So then you can get, for approximate values, you can show that. This is what we get. Okay. So now we can just, we can compute. Once we have n plus bar, we can compute m and chi. Okay. So m mu tilde b into n into r. Okay. And chi is just a derivative of that. Okay. This is at low temperature. High temperature is even simpler. So this is low temperatures. At high temperatures, mu is just given by the ideal gas thing, right? So mu is, so what you will get is mu is just we usually don't write it like this, but we write it as z, which is e power beta is equal to lambda cubed upon v. So it's the same thing. Okay. So you can go ahead and solve, and we can put this in. And this implies that r equal to tan hyperbolic mu tilde b by kbt. Okay, for small b, this is okay. And from this, we can show that chi at high temperature is equal to n1 into but I think if I want to compare with the other answer, mu tilde has this thing, right? So this will be equal to 1 by 4 mu b square by n by kbt. Okay, it's still 1/4 is still greater than 1. Okay, so this is paramagnetic. Okay. So chi total will be 1/4 minus 1/12. Hopefully this is all correct. So then what? 3 minus 2, so it is. Okay. So I've jumped some steps, but I mean, once you have this formula for mu, you can just plug it in there and this is the solution. It's not hard. Okay. So that sort of concludes what we have seen. So we have seen three features. So we did of a Fermi gas in the presence of a magnetic field. Okay, the first one was Landau diamagnetism. This was high T story with only the orbital, high T with orbital part story only. Then the second one was the De Haas Van Halphen effect, which shows that various discontinuous curves, right? I mean, this is T equal to 0, again orbital. And the last one is Pauli paramagnetism. Okay, and this is just the spin contribution. Okay. So you can, the total, if you're working with a metal, you can't go around separating these things. And if you're going to do with an experiment, you have to add all these contributions. But for instance, the D has one alpha effect is very interesting because it says that there'll be discontinuities. And so the other effects are like continuous, smoother. So you will see these funny effects. You should be able to see. Okay. So I'm done with the course. So thank you. And are there any questions online?
Sir, last lecture will be uploaded, right?